Okay, let's jump into another example here. So we're going to find the limit as t goes to 0 of this fraction that we have here. So the numerator is the square root of t squared plus 9 minus 3, and the denominator is t squared. Well, it's worth just checking like we did last time. Let's just check what would happen if you plug in t equals 0. Just right off the bat, just see what happens. If we plug in t equals 0, well, we would get 0 squared plus 9 underneath the square root. So that would be like the square root of 9, which is 3, but then you subtract 3. So the numerator would be 0. And if you plug t equals 0 into the denominator, you'd have 0 squared, which is also 0. So it would be another 0 over 0 type. So that's just in case, it's worth checking. That doesn't really help us, but it's good to be in the habit of just checking at the beginning of your limit calculation. Okay, well, what are we going to do? Well, we can do some work on this limit as t goes to 0. And we just copy down what we started with. T squared plus 9 minus 3 all over t squared. So that's our limit, just that we started with. Now what are we going to do? What's our first step going to be? Well, remember when we talked about rationalizing the denominator in section 1.2, and it was a technique that you can use to remove radical symbols from the denominator? Well, there's no reason you couldn't use the same technique to remove radical symbols from the numerator. Now, what would that look like? Well, it comes down to multiplying by the conjugate. Right? We're going to multiply the top and the bottom of the fraction by the square root of t squared plus 9 plus 3. So what we'll get is the following. Root t squared plus 9 minus 3 all over t squared. So this is just the original fraction that we had. And now we're going to multiply by root t squared plus 9 plus 3 on the numerator and denominator. Okay, so that's what we get. Now, what's going to happen if we actually perform that multiplication? Well, remember, you multiply the numerators to get the numerator of the result, and we'll multiply the denominators to get the denominator of the result. And really what we're doing is we're setting up a difference of squares. So the new numerator, when we perform the multiplication, let's work out what the difference of squares would be. If you actually multiply the numerators, this is what you're going to multiply. And, well, it's like a minus b times a plus b. So you're going to get is, well, you're going to get root t squared plus 9 all squared minus 3 squared. And then what ends up happening? Well, the squared and the square root cancel. So what you end up with is t squared plus 9 for the first term. But then what happens over here? You're going to subtract 9 because 3 squared is 9. So you actually have a minus 9 afterwards, and you end up with just t squared. So that's actually what your numerator is going to be. These two expressions multiply to t squared. So the next step is going to be the limit as t goes to 0 of t squared over t squared times the square root of t squared plus 9 plus 3. Okay, so I'm going to clean this up a little bit because it might be hard to read. Okay, so you got this left over. So this is just the square root of t squared plus 9. Just this expression here is left over here. Now, it's still a 0 over 0 type, right? We've definitely rationalized the numerator. There's no radical signs in the numerator. But now, whenever you do something substantial to your limit function, you should probably just run through the calculation again. Ask yourself, what would happen if you plugged in 0 to the whole fraction? Well, this time you're still going to get 0 over 0. Because if you plug in 0 here, you're going to get 0 squared. And then you plug in 0 on the denominator, well, you're going to have 0 squared over here. So it doesn't matter what this is, you're going to have 0 on the denominator as well. So it's still a 0 over 0 type. But you have a common factor now in the numerator and denominator of t squared. So we could actually cancel out the t squareds. And the numerator is just going to become 1. So what we're left with now is the limit as t goes to 0 of 1 over root t squared plus 9 plus 3. Okay, so, well, now what happens if we plug in t equals 0? Well, the numerator is 1. If you plug in t equals 0, we're going to get 0 squared plus 9 inside of the square root. So that would be the square root of 9, which is 3. But this isn't minus 3, it's adding 3. So it's actually, you'd have 3 plus 3 on the bottom, which is a sensible number. So that looks like we're ready to just plug in our value now. So we're going to get 1 over the square root of 0 squared plus 9. This is what it means to actually take the limit. So now, notice now I'm not writing limit as t goes to 0 anymore, because from this step to this step, I've actually taken the limit now. Okay, so what ends up happening? You just get 1 over, run out of space here, 1 over root 9 plus 3. So that's just 1 over 3 plus 3, so 1 over 6. And then finally, that's our answer. Okay, so that was great. That worked out. Let's look at the next one. And the comment above says, finding a limit often requires investigating one side at a time. And what that means is, when in doubt, you may want to drop to the level of just considering one-sided limits. Okay, so for example, if I'm taking the limit as x goes to 0 of the absolute value of x over x, well, what happens if you just plug in 0? Well, you'd have the absolute value of 0 divided by 0. Right? So we would have 0 over 0. So it is a 0 over 0 type. And you can't cancel the x's here because one of them's inside an absolute value. So unlike in the previous example where we canceled the t squareds and that actually helped a lot, this is probably at the turning point in this example where it suddenly seemed solvable. But in this case, we can't just cancel those x's because one of them's inside an absolute value and the other one's not. So they're not the same thing. So what we're going to do is we're going to consider the one-sided limit. So we're going to take the limit as x approaches 0 from the left of the absolute value of x over x. So same limit, but we're just going to take one side at a time. So what happens as x gets closer to 0 from the left? Well, now we can actually do something. Because remember, let me remind you, by the definition, the absolute value of x is one of two things. It's just x if x is greater than or equal to 0. But if x is negative, then the absolute value of x is negative x. So that's how the absolute value function works. And since x is approaching 0 from the left, this means the values of x, as far as this limit's concerned, the values of x that we're looking at are negative. So that means this absolute value of x can actually be replaced with a negative x. So we get negative x divided by x. And now that absolute value is dealt with. So we can cancel the x's. So if you cancel the x's, we get the limit as x approaches 0 from the left of negative 1. And now we have the limit of a constant. And remember, in the very first, one of the very first observations we made in this section is if you had the limit of a constant, that no matter where the variable is going, this limit always just evaluates to whatever that constant is. So we're going to get negative 1 for this one-sided limit. But be careful, right? This is just as x goes to 0 from the left. So don't fall into the trap of thinking you're done and putting a box around that, because we're not done, right? We haven't found this limit yet. We've only found the one-sided limit. Let's find the other one-sided limit and see what happens as x goes to 0 from the right. So we'll take the limit as x goes to 0 from the right of the absolute value of x over x, and we get what? Well, as x approaches 0 from the right, the values of x that this limit cares about are positive. So that means this absolute value of x will be replaced with just x, since the values that our limit cares about are positive. So we're actually just going to get x over x this time. And now, still, we can cancel the x's, and we get the limit as x goes to 0 from the right of the constant 1. And again, we have a limit of a constant. Doesn't matter where the x is going. If we're taking the limit of a constant function, the result is just going to be whatever that constant is. Okay, so now we've finished. We took the limit from the left, and we got negative 1. And we took the limit from the right, and we got positive 1. So what does that mean about the two-sided limit? So we can say, therefore, the limit as x goes to 0 of the absolute value of x over x does not exist, right? Because if the two one-sided limits don't agree, that means the two-sided limit does not exist. So that's how we can finish that example. And quite often, if you're doing an example with an absolute value, you'll probably have to follow this exact same approach and take the limit from either side at a time. And then once you find out whether the two one-sided limits agree or not, then you can conclude, well, you can draw your conclusion accordingly, right? If these had been the same, like if they were both -1, for example, then we would have concluded that this limit is -1 as well, right? If they were both +1, then we would have concluded that this limit is +1. But since they were different, the two-sided limit does not exist. Okay. Another example of when you might want to take limits one side at a time is if you're dealing with a piecewise function. So here we want to calculate the limit as x goes to 4 of the function f of x, where f of x is given by these two rules as a piecewise function. And another hint is if the value you're taking your limit near, or if the value that your variable is approaching, if that value happens to be precisely the point at which your function changes behavior, then you know you're definitely going to want to take one-sided limits first. And that's exactly what happens here, right? It's at x equals 4. That's the point at which the function changes behavior. But and this is where we're taking the limit towards. Notice that this function is not actually defined at x equals 4. Right, there's no definition. If x is equal to 4, this function f of 4 is undefined, because if x is equal to 4, neither of these rules are satisfied, so there's no output formula. So f of 4 is undefined. But we can still take the limit as x gets close to 4, because remember, the limit doesn't care what happens when x actually gets to 4. You don't actually care what happens at x equals 4. You only care what happens when x gets close to 4. So without further ado, let's take the one-sided limits. So we'll take the limit as x goes to 4 from the left. And what happens? Well, here's now we can use the fact that we know what f does on each segment of the real line. So limit as x approaches 4 from the left, this means that the values of x we're considering in this limit are all less than 4, because that's what it means to approach 4 from the left. So if the values are less than 4, that means for all the values that this limit cares about, f of x is always equal to 8 minus 2x, because that's what f does for input values that are less than 4. So we're going to get the limit as x goes to 4 from the left of 8 minus 2x. And now we don't have, or pardon me, this is a polynomial, right? 8 minus 2x. That's a polynomial, a degree 1 polynomial, and they have the direct substitution property. So we can go ahead and just plug in our value now to get the limit. So plug in 4 for your x, and then you're done. So we're going to get 8 minus 2 times 4, which is 8 minus 8, which is 0. Great, so that one-sided limit worked out to be 0. And now we're going to take the other one-sided limit. So take the limit as x goes to 4 from the right. Okay, we'll see what happens. So how do you do this one? Use the same approach, right? The limit as x approaches 4 from the right, that means the values of x that we care about are all greater than 4. So that means for the purposes of this limit, this function f of x is going to behave exactly like the square root of x minus 4, because that's what f does when its input values are greater than 4. So we can take it one step further and be more specific. This is the limit as x goes to 4 from the right of the square root of x minus 4. Okay, and now we can actually plug in our value. We can plug in our value of 4, and we're going to get the square root of 4 minus 4, and we're going to get this, that's the square root of 0, right, which is just 0. So great. We get 0 for both of the one-sided limits. So now in this case, unlike the previous example where the two-sided limit didn't exist, because both our one-sided limits agreed and gave us both 0, we can say therefore the limit as x goes to 4 of f of x is equal to 0. So that takes care of that.